Good evening, everyone. Welcome to the third and final day of our online session. I would like to start by extending a warm welcome to our esteemed speaker, Mr. Sankeet. Thank you for joining us again and for sharing your expertise with us. To all our participants, a big welcome back. It's great to see you all returning for the final day of this session. I am excited for the insights and learning opportunities that today will bring. Without further delay, let's get started. Handing over to you, sir.
Yeah. So today we will be covering counters, shift registers, then FSM. With we'll be taking an example of a sequence detector. Then top circuit. Then FIFO is will be covered. Then in the last module, uh, system task I will take. How to write the test bench, then how to give the delay, those things I have discussed. So counters. We will be having up counter, down counter, then up down counter, then mode and counter, then ring counter, then Johnson counter. So these many counters we have. The Verilog part of this counter will be counting like 1, 2, 3, 4, 5. Like that it will count. So according to the how much bit we are taking, it will count till that. Suppose we are taking a 2 bit, then it will count from say 0 to 4, 3. So the counter design, we will start with up counter. So same as module, giving up. Then we will be requiring input as clock. We need a reset. Then for counters, other than clock and reset, any other inputs won't be there. So we have an output. Let's take it as a 4-bit counter. So it will be 3 down to 0 count. So these are our inputs and outputs. Then starting with always percentage of clock. Yesterday I put comma here. Instead, if you want to like say instead of comma, you can use or also. Or negative of result. Begin. If negation of reset, which means that negation is high, means reset is high, then count will be 4 tick V 0 0 0 0. Else count will be count plus 1. You can write 1 or you can write 4 tick B 0 0 0 1. That is also fine. Okay. Then end. End. So it will count like this 0 0 0 1 0. If you are giving reset, then it will start like 0 0 0 1. Then it will be 0 0 1 0 0 0 1 1. Likewise, it go up till 1 1 1 1. Then again it will go back to 0 0 0 0. Okay, that is up counter. Down counter is similar. Only difference is when we are resetting, then it will become 4 tick B 1 1 1 1, and here instead of count plus 1, it will be minus 1. So for down counter, these all are similar. Okay, input will be clock, reset, and output we have 4 bit of count. We are checking for positive edge of clock or negative edge of reset. Then for the reset part, inside that always I'm writing what is the difference between up counter and down counter. Count will be for tick B 1 1 1 1. Else count will be count minus 1. So only this part is different from up counter to down counter. Any doubt in this? You can try for down counter. I have written for reset 1 1 1 1. Instead, you can try 0 0 0 0 also when you are designing, and only the difference will be instead of plus there will be minus in this code. That code also you can write. Okay. The next one is up down counter. For up down counter, there will be an input like whether it should be an up counter or down counter. It is decided by a mode. So we will be having another input. So module up down input clock reset input mode, and we have output of reg type 3 down to 0 4-bit count. Always. So most of the counters we will be using asynchronous resets. The next thing is mode counter. Say If you are taking a 2-bit counter, so we will be having 0, 1, 2, 3. These are values, right? 0, 0, 0, 1, 1, 0, and 1, 1. Right. So if I am saying like these all are stable states, how many stable states are there? Accordingly, we will say that it's modulus. Okay, if it is mode 5 counter, it will have a 5 state. After that, it will go to the reset. Whatever initial state was there, it will go to that part. So let's take an example of mode 5 counter. Module mode 5 counter. We have input clock, reset, output right, way down to 0, count, always block, always set, percentage of clock or percentage of reset, begin, if reset, count will be 0, else inside that we are checking again if count equal to 4 tick D4, which means that it will be having 5 stable states from 0 to 4. So that's why I'm checking our count is 4 or not. So I'm using an equality operator and checking that count is 4. If count is 4, then we will be resetting it 0, 0, 0, 0. Else, we can either take mode 5 up counter or mode 5 down counter. Here I am taking up counter. So count plus here begin should be there and and and, and. Any doubt in this?
Sir,
Yeah.
sir, like mode 5 counter counts up to 5 or counts up to 3.
Counts up to 4. It will be having 5 stable states.
Okay, so the output will be 4 down to 0.
No. If it is 3 down to 0, which means that it have 4 bit. 4 bit means you can go from 0, 0, 0 to 1, 1, 1, 1. Right. To the power of 4. This many states are available, but we are only taking up to 4. Clear or any doubt is there? This is the size.
Yes, sir, I understood.
Any other doubts?
No.
Ring counter. So what the ring counter do is just we will be having let's say 0, then 1, then 2, then 3. Again we will be going to 0. It will be a kind of ring kind of. Okay. So I'm taking a different kind of ring counter. So let's say I want a ring counter like this. So after 1, 2, 3, 4, 4 states, it's again go to the initial state. So this kind of counter I want to design. So we will be using left kind, what do you say, rotate kind of operation here. We are rotating this 1, 2 here and giving this 0 to here. Understood? So similar kind of thing we can do in Verilog in similar way. I will explain that. So let's say we want to design a ring counter. It have input clock, then reset, output of its type of size 4-bit out. Okay. Then we have always block at 4 sets clock or 4 sets reset. Begin. If reset, out will be 0, 0, 0, 1. That is our initial state. So I am resetting to that state. Else, we are saying like we need to rotate. So for rotating, what I am doing is I am taking the last 3 bits and shifting that to here, and I am giving the last bit, it's this 4th bit to the LSB. So it will be like concatenation of this. Understood this? Should I explain what I have done here? So what we want is we want let's take these 2 states. What is the difference is this we are shifting to front and this we are giving to here. This we are giving to here, right? So the same thing I have given. So output I am changing and concatenating that with these 3 bits I am giving as MSB, and the last our previous MSB I am giving to LSB. Understood? So when you are guys are dealing with this in digital electronics, there is ring counter, Johnson counter, all will be discussed in D flip flop using D flip flops. So D flip flop can be converted into a counter. Same frequency divider also you can design with D flip flop. So that frequency counter means frequency divider I will explain with EDA background. Then you will get one get an idea. So ring counter you got. So the thing is, whenever we are getting a like different cases, if we want to design one, then we want to design 0, 1, 0, 1, then 1, 0, 0, 1, then 1, 0, 1, 0, then 1, 1, 0, 0. So here what I have done is, first I have taken this one and shifted that to the end. Then the last one I shifted that to the this thing. So this thing, if you want to design in Verilog, you can design that. After that, it will again this first 0 I am taking again back. So it will become 0, sorry, 1, 0, 1, 0, then 0, 1, 1, 0. Then this 0 I am taking. So 0, 1, 0, 1, then 0, 0, 1, 1. So it will having 1, 2, 3, 4, 5, 6, 7, 8 stable states. So if you want to design a systems having different kind of combinations of what is it pattern, then you can use this concatenation operation and what particular bits are standing at the same position in the next, or any of the bit is changing to the left or right, you can accordingly you can use this concatenation operation. Okay. So try it as an exercise. You can design this. This pattern you guys try as an exercise. Okay. Then we have twisted ring counter, otherwise known as Johnson counter. Johnson counter or twisted ring counter. So what the difference between ring counter and Johnson counter? Uh, so let's say I'm taking 3D D flip flop. This is the clock. Which is common and it is positive edge. If it is negative edge in the design, you can see a bubble. Okay. Then we have negative edge of reset. So as ring counter, we will be connecting. So we have D as an input, then Q and Q bar as output. So we are taking Q and connecting to the D or D2, let's say D1 Q1, D2 Q2, D3 Q3. So this is what a ring counter does. Instead of taking from Q3, if we are taking from Q3 bar and connecting to D1, then it will become Johnson counter. Okay. So what that means is the first LSB bit that we will be giving to MSP as negated one. When I write the code, you will guys get to know more. Okay. So write module Johnson counter. We have input clock, then reset, then output rise time of 3 down to 0 out. Always at search clock or naked reset RST begin if negation of reset out will be 0, else what we have to do? We have to take the Q3, right? So if it is 3 down to 0, we need to keep that 3 down to 1 as same, and whatever 0 is there, that we need to give as MSP, right? So it will be negation of 0. So this will be the new updated one. So how we will give that? Out concatenation negation of out of 0, then out 3 down to 1. End and end. So what we have done in the first cycle, we are resetting. So Q1 contains 0, Q2 contains 0, Q3 contains 0. Okay. So the output is 0, 0, 0. One more D flip flop we need. 1 second. One more is there. Okay. D4, Q4. Otherwise, I put the same label. Will be D1, Q1. Will be D2, Q2. This will be D3, Q3. Okay. So we are connecting these two here. Q3 bar. So when we are given reset signal high, so Q0 was having 0, Q1 has 0, Q3, Q2 has 0, Q3 has 0. Okay. In the next cycle, we are giving Q3 bar to D0, right? So the Q0 will have the value of 1 now. This 0 came here as twisted 1. Then the Q3 value shifted to Q1. So it will give to here. So it will be 0, given to here to 0, and given to here it's 0. And it is given with NOT gate to here. So that's why it came 1. So this is the first positive edge. No, this one. This one is the first positive edge. And the next positive edge, again, this 0 will come negated to the MSB 1. So it will become 1. And this 1 is shifted to the next D flip flop, 0 shifted to the next flip flop, this 0 shifted to the next flip flop. And in the next cycle, it will become 1, 1, 1, 0. And in the next cycle, it will become 1, 1, 1, 1. and again it will go to, I'm writing here, okay, it will become 0 1 1 1, then 0 0 1 1, then 0 0 0 1, then all becomes 0 0 0 0. So this is what happening in a Johnson counter. So the same code we have written here. We are just giving the negated of the last LSP to the MSP and keeping the other bits as same. Any doubt? Understood? Ring counter, Johnson counter, what are the difference? Why we are using negation of reset is we are taking the negative edge of reset, right? So if you are writing only reset in the if part, it's checking for what? It's checking for whether reset is 1. And it won't happen in a negative edge of reset, right? We need the negative part, which means we need this. So we need to check the 0 for the reset. That's why we are giving negation of reset. We are checking 0, whether reset is 0 or not. In other case, whenever negative edge of reset is there, we say that whether reset is high or not, which means that reset is 0. So according to the sensitivity list, we are giving this negation. If I am using positive edge of reset, I have not used somewhere above code. Here, positive edge of reset is there, I have not used negation. We need to check here reset is high or not, which means that reset is 1. Here, reset should be 0. That's why I'm using negation. Clear? Arundhati?
Yes, sir.
Any other doubt? Okay, let's take. So I want to explain how a D flip-flop works as a frequency divider. So we will write the code for D flip-flop. We have input clock, then input reset, then we have input D, then we have output regs type Q. I'm not taking Q bar. If you want, you can take Q bar also as an output. There will be 2 outputs in a flip-flop. I'm not taking. For reset, percentage of clock, or let's reset again. If this negation of reset is high, then we say Q is 0, else we say Q is D. And module. Okay, so the response for this is module TB. We have like type of clock, RST and D, and wire type of Q. Then we need to instantiate D flip-flop I'm taking D1 as that. Then I am taking name. So clock of clock, then T of T, then RST of RST, then Q of Q. I'm taking initial block. Inside I'm giving clock as 0 first. I'm giving reset high. Then after 10 nanoseconds, I'm giving reset 0. Then after 10 nanoseconds, I'm giving reset again high. Then after 10, no, at the same time, let's say initially I have not given D anything. So let's say otherwise we'll get that. So these conditions you can change according when you are doing the simulation. What all conditions you want, you can accordingly adjust these things, and you verify whether the code is working according to our conditions. Okay. So I'm giving according to my idea. So you don't need to copy this exactly. You can try different one. Then after giving, I will give D1, and after 5, I will give D0, and after 8, giving D again 1, then end. Then we need to give another initial begin block which contain that dump file. You remember, right? So for that, we are using dump file of dump VCD format. Then we are storing all the variables. Then after 100, I'm calling finish. And then always hash 5, I'm taking clock equal to negation of clock. End. And module. Today I'm using Aldic. Then open EP wave. Running this. Okay, yesterday I explained how this is working. So here we are taking negative edge of reset. That's why for negative, even if reset is high, is not turning Q as 0. So it will detect only the negative edge of the reset. At that time, it is changing the Q value to 0. Even we can see here, one positive edge of clock is here, but inside that, always block will get executed. At that time, D value is X. So Q value will be also X. In the next positive edge, D value is X, but Q value is 0 because reset is 0 there. That's why it is getting resetted here. In the next positive edge of clock, our reset is become 1. So whatever value we had in the D, that will be stored to Q. So here D value is 0. That's why Q is also 0. The next positive edge, again reset is high there. So Q will be D, right? So D will, here is 1. So Q also 1. So it's working as a D flip-flop. Now what I want is, I want to convert this into a frequency divider. Can anyone tell me what will be the difference? So for a D flip-flop, if it need to be a frequency divider, let's say this is D flip-flop. Clock is there, reset is there. Whatever output we are giving, that should be negated and given to D. So this D flip-flop is acting as a frequency divider. So how it is working, I will explain with this. Okay. So we won't be requiring this input D. We will be only requiring output, let's Q bar. Still, I'm not using Q bar. Let's say I'm dealing with Q only. So instead of D, we will be giving negation of Q. Sorry. So only thing we need to give is reset and clock in the initial begin block. And after that, every 5 we are negating the clock. So the clock signal will be get generated, and initially I'm giving reset. Okay. After that, I am giving. So D is not required here. Okay. Now let's. So till here, because of reset is 0 here, so Q will be 0, right? So we are giving reset, and in even positive edge is there, still reset is there. So that's why we are giving still the Q is 0. So in the next positive edge, whatever previous positive means Q was there, that is 0, right? So it will become Q bar. So it will become 1. And in the next positive edge of clock, it will become 0. Next positive edge, it will become 1. The next positive edge, it will become 0. Then again 1, 0, like that. So as you can see here, whenever the reset is not there, if reset is out, then our output is becoming 1 for one entire clock cycle, right? So here the frequency is divided by 2. You are seeing this? Likewise, our Q is becoming 0 for entire clock. So in this, if our clock is like this, our output will become like this. So this is frequency divided by 2. So likewise, you can design different frequency dividers. If you are connecting one more here, one more D flip-flop, and this output you are giving to here and taking the negated one and giving this, not this one. So the twisted ring counter, what we have studied, Johnson counter. So that D flip-flop will act as a frequency divider. You find out how the design is working. So you guys got an idea, right? So our counter design, whatever we are given here there, for all the counter, the test bench will be the same. We have clock, reset, and output. Instead of Q, I have used count somewhere, out somewhere, that you can change accordingly. Okay. Any doubt? Any doubt in this frequency divider? How it's dividing? So I'm covering like light speed. I want to cover most of the topics that is commonly used to design in Verilog. So you guys will be familiar. That's why I'm taking all the things. This is serial in, serial out. So we are moving to shift registers. Okay. So I will write the code first. We have CISO, input, clock, input, reset. Then we have an input of D in. Then we have out, D out. So I'm not taking it as a register type. I'm separately defining one register data here, reg data. Always at percentage of clock or percentage of reset begin if reset, our reg data will be 0. Reg data will be 4 down to be 1, 2, 3, 4. Else I'm shifting that reg data will be, so in the LSP part we will be including our DA. So all other thing will be similar. So reg data 2 down to 0. Then the MSB will be discarded, and then the LSB we will be adding DA. So every positive edge of clock, whatever DN we are giving, it will be added in the LSB and it will get shifted. Then I am assigning. So it is serial in, serial out. So whatever MSB at the end of this cycle, we need to take it as an output. So every time our output will be taken from MSB. And okay, let's say what serial input, serial output means. We will be giving value at one side and we are taking value from other side. So initially it was 0, 0, 0, 0. Let's say I'm giving D1 1. So it will become 0, 0, 0, 1. After that, I will become giving 0 or 1. Let's say I am giving 0. So 0, 0, 1, 0. Then again 1 I am giving. Then it will become 0, 1, 0, 1. Then again I am giving 1. So 1, 1, 0. Sorry. 1, 0, 1, 1. So in this part, our output will be 0. 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 In the next cycle, if I am giving again 1, so it will become 0, 1, 1, 1. Here, our output is 1. So whatever discarded, that coming out of this from the MSB, that is given as our output, Out. So this is simple serial input and serial output. Any doubt on this? Because of serial input, serial output, we are taking it as 1 bit, 1 bit. So in the next design FIFO, which means that serial input, parallel output, the design will be different. Will become module FIFO. We have input clock, reset, serial input. So 1 bit in, parallel output. So we need to take, let's say I am taking 4 bit. So it will be 3 down to 0 D out. So this is serial input. This is parallel output. Okay. So that's our input output. Then we have we need to define one reg part. So I am taking a reg 3 down to 0, reg data. Then always at posets clock or posets reset begin if reset are not given entirely here. So you can change this. Okay. Our reg data will be 4 tick B 0 0 0 0. Else what we have we are serially giving, right? So it will be similar to what we have written above. Reg data 2 down to 0, then DA. But the change will be in this D out assignment. What D out will be? D out will be reg data. So entire 4 bit we will be getting at each cycle. So the diagram will be like this. 1, 2, 3. Okay. We are giving serially, but we are taking all at once to D out. So this is what happening in FIFO. Any doubt in this? No doubts? Likewise, you can try for FIFO and FIFO. FIFO is not exactly a shift register. That is the most simplest shift register actually. Parallel in, parallel out. It's kind of delaying that. Whatever value we are giving, it delay for some time and it will take the output as it is. FIFO will be a little bit tricky. So that you guys take it as an assignment. There will be a load control also. According to that, we need to design. Okay. So any doubt in these shift registers? If you want, I will give an idea what PISO is. So PISO means parallel input, serial output. Okay. So the diagram whatever I'm drawing here, it is not exactly what you guys will be learning in digital electronics. I'm drawing it for explain purpose. So we will be giving parallelly what as input. So this is our input. And we will be taking as this as output. Okay. So the thing is, we need to understand when to load the data and when to take the data. So there will be a control signal that will be in between this input and this particular D flip flop. So most of the design, it uses different kind of gates. We can use OR gate or AND gate. Even if you are searching in net, you will get different diagrams. Okay. So there will be a load. So if load is high, let's say we are loading the input into this. When load is low, we are taking the output. Again, if load is high, we are loading. And when load is low, we are taking the output. So whenever load is low, we need to take the output. That's the thing, nothing else. So this decides whether to load the data or take the data. So that is the tricky part in PISO. Okay. So moving on. For FIFO, actually, the thing is, if I want to explain FIFO in depth, it will require so much time. So there are so many signals. With the time limit, I will explain a simple code. So you will get an idea what is FIFO. So FIFO full form is first in, first out. So uh, we will be having a module FIFO and this all signals I'm taking. Then we have reset. Usually when we are packaging the industries, if it is negative, we usually put like this to understand with the signal name itself, we can understand, okay, it is negative and it's triggered. If we are writing like this, it will be positive and it's triggered. So you can uh, use like that. Here I am using positive edge, so I am giving like that. Then we have write enable. Then we have read enable. Then we have let's take 8-bit. So 7 down to 0 of our data in. Then we have an output of same register type of 8-bit. So 7 down to 0 data out. Then we have two flag signals. We have output reg pull and output reg empty. So these are two flags. When the FIFO is empty, we don't contain any data, the empty flag will be high. And if it is full, then the full flag will be high. Okay. So I am taking a memory register and it is having 7-bit, means 8-bit data, and it have 8 locations, which means that this is our memory register. Check. It have 1, 2, 3, 4, 5, 6, 7, 8 locations here. 1, 2, 3, 4, 5, 6, 7, 8 locations we have. And in each location, we can write up to 8-bit of data. So each location have 8-bit, 8-bit, 8-bit. So that this means this is actually 2D representation. So if we are writing 7 down to 0, A of 3 down to 0, this means that A have 7-bit of data and it have 4 locations. Sorry, 8-bit. 8-bit of data, 4 locations. So that what I have represented here. So it is a memory. It have 8 locations and 8-bit. Then we need a write pointer, read pointer. I'm defining it as 3-bit write pointer. Then read pointer. Because of 8 location, I am taking 3-bit. Okay, so we need to cover entire locations. Then I'm taking an always block always at 4 sides of clock or 4 sides of reset if begin is there, if reset, then we are saying right pointer will be 0, read pointer will be 0, then full will be 0, empty will be 1. Okay. Also, if you want to erase entire data what that are represented in memory, you can put memory also. Mem 7 down to 0 will be 0. Not like this. Actually, you need a for loop for that. Each location you need to write. Okay. So I will explain how to write that. So before explaining that, I will explain this part. Okay. Uh, so in reset, we are resetting right pointer to 0, red pointer to 0, full will be 0, empty will be 1. Memory I am not resetting now. Then I want to read first. Okay. If read enable is high and empty is not 1, you can either use this or negation of that. No issue, because our empty is 1 bit. So 1 bit logical and what bitwise is similar only. Begin. I'm saying our data out will be wherever our read pointer is there, that particular location we have to read from memory, and we are giving that to data out, and our read pointer will be getted incremented. Read pointer plus 1. If we want to do the right part, then if write enable and then not full. If full flag is there, we won't be able to write the data into the FIFO. Then to that particular memory location of where the right pointer is pointing, our data in will be given. And our right pointer will get incremented. Okay. So if I'm taking one count as a register, like reg 2 down to 0, 3 down to 0, number of elements. Okay. I want to find out how many number of elements are there in the FIFO. So whenever write is taking place, our count will get incremented. Count plus 1. And whenever read is taking place, our count will decrement. Count will be count minus 1. Why I am taking count? We need to mention our flag. Whenever when the flag is getting high, or when the full flag is getting high, or when the empty flag is getting high. So we will be having 3 down to 0, right? So it will count till to location 8. So whether it's checking like all the locations have the value. If all the locations have the value, which means that count equal to 8, then it will become 1. So full will get 1. And for empty, we will say like when the count equal to 0, which means that it don't have any value in any location. and for the else part, and for the always block, and for and what we are doing is we have read enable, write enable, clock reset, data in, data out, full empty. These all are our ports, and we are taking a memory, and we have write pointer, read pointer, and count. So in the positive edge of clock and positive edge of reset, if reset is high, we are saying like write pointer, read pointer, full empty will be resetted, and empty will become 1, all other will be 0. And if read enable is high and empty is not high, which means empty is 0, then which means that the FIFO is already have some values if empty is 0 means. Right. So we can read. That's the thing. That's the logic here. At that time, wherever the read pointer is pointing in the particular memory, from that memory location, we will be taking that data and giving to data out. And our read pointer will get incremented by 1. And in that case, we are counting count equal to count minus 1, which means that one data is already read out. So that data is not there now. Like that. Okay. Then when the write enable is high and full is not present, then we can write into that FIFO. We can write the into that particular write pointer location of the memory. We will be giving the data in, and the write pointer will be get incremented by 1. And at that time, count will be count plus 1. So if count is 8, which means that all the locations have values now. So FIFO is full. So FIFO full flag will be become high. And if it is 0, which means that all the locations have read out or not written anything. So it will become empty high. This is the simple code. There are so many other things you can include. You can include depth. Then this can be made it as a parameterized thing. These all things you can go for. If you are going in deep, you can refer that. Okay. So you got an idea how the FIFO works? How to do the 2D representation of memory? How to reset the memory, I will tell you. Any doubt? So if you want to reset the memory, so what we have to do is inside the reset only, you can give a for loop for I equal to 0. We have 8 locations. So we need to give less than 8, I plus I equal to I plus 1. Begin mem of that particular location, we are giving 8b0. And so this you can include here. Okay, this part we can include here. To declare that I, we need to mention before always block, we can mention here integer I. Okay. So that's how we erase all the data that are present in the memory. And this is the working of FIFO. Any doubt in this? Okay. So the sequence detector, you guys try to explore. Now you will be able to understand the code. FSM is a little advanced thing, so it will require another 20-25 minutes to explain that I am not taking now. So in this, we have covered these counters, shift registers, and FIFO. This FSM, uh, you guys learn about FSM first. Then there will be two finite state machines as well, Mealy and Murray. Then there's a difference between this and how to represent that in the state diagram, and with that how to write that truth table. Till that, if you are able to do, then Verilog part is simple. So to explain that, I require more time. No issue till up to here, from the starting of this course till here. Any doubts is there? If you don't have any doubt, you can put no also. If you don't have any doubts, you can put no in the chat. If you guys have any doubts, you can ask that. I will clarify that. Which all semester students are here? First year is there, then third semester is there, then any fifth or sixth, seventh semester is there? Fifth is there. I think in fifth semester we have one course like VLSI something is there, right? VLSI design. I don't know. In curriculum, I think Verilog is added in K2, right? In which semester you are learning this Verilog part? S3 only. Okay. So for fifth semester and seventh semester students, will be easy for you guys. You already understood all those things. Okay, for third semester students, now you will be getting an idea whenever this Verilog part is taken in your class. You will be understanding much more. Okay, you can revise, or if you have any doubts, you can ask me, or you can mail me, or WhatsApp number is there with the uh, coordinators. You can ask them. If I am free, I will help you guys. Try to practice this Verilog through HDL bits. I will show you that. So you will be having a problem set in that these all are questions. Okay. So if you are clicking, for example, I am taking an AND gate here. So it will be giving a problem statement. You read this first, and this is our top module, and these are the inputs and outputs. So they have declared already all the inputs and outputs. What we have to do is we need to design that. So if I am writing assign out is equal to a and of b and submit this, what will happen is they will execute this and they will plot a simulation graph. If it is with the reference and ours is similar, then mismatch won't be there and it will be getting status of success. And if I am doing some other things, like if I am using OR gate instead of and I have done the compilation, now you can see status is incorrect, mismatch is there. So likewise, you can practice. Okay. There are more than 50 questions are there. So if you are getting time, try to do that. For seventh semester, if you are planning to go to that VLSI domain, whenever you are getting an interview, these all things will be asked. Even you can mention this HDL bit in your resume. Some interviews, they directly tell you to open this HDL bits and solve one question. They will tell you which question that you have to solve in front of them. That also happens. All the basics you have to cover, okay? Okay, let's wind up then. Any doubts is there, then you can stay and ask. Otherwise, we can.
A sincere thank you to everyone who participated in our 3-day online session. It was a truly pleasure to have you all with us for this enriching and insightful journey of learning and growth. We would like to express our deepest gratitude to our distinguished speaker, Mr. Sankeet, FPGA engineer at Tejas Networks, for graciously sharing his time, expertise, and valuable insights. Your sessions were both informative and inspiring. Thank you for making this event a memorable one. As a token of our appreciation, we are delighted to present an e-memento to Mr. Sankeet in recognition of his valuable contribution to this session. To all
Thank you.
our amazing participants, thank you for enthusiastic engagement, thoughtful questions, and commitment to learning. Your active participation made this event truly interactive and impactful. Please make sure to fill the feedback form, which will be shared in the WhatsApp group. Until next time, thank you once again and have a wonderful day.